Well, it's that time again. Thought I'd see if I could wake you up one more time. Your stockbroker tells you that your stocks fell 50% yesterday, but don't worry, they went up 50% today. What should you do?
Pull them out.
Fire the stockbroker. How about it? This stockbroker is losing you a lot of money. What you have is an amount A, and if it goes down 50%, you've got 1/2 of that, right? But now if it goes up 50%, you get 3/2 of what you had. And so now what you've got is 3/2 times 1/2, or 3/4 of the money you started with. You just lost 25% of your money. You should worry, right? Fire the stockbroker. Anyway, there's a good math question for you. Just to start off. Well, tonight we want to pick up where we were last time on finding maxima and minima. Pretty fun stuff coming up because it's real beautiful pictures and nice applications. We have this. Suppose f of xy is x times y on the unit disk. X squared plus y squared less than or equal to 1. Find the maximum and minimum, meaning absolute or global maximum and minimum, not just a relative max or min, of this function on this region. How can we do that? Or what the theorem was last time? It's been a long time. What does the theorem say about this kind of problem? Said if you have a continuous function, how do I know this is continuous? Well, what you do is you say you have all those theorems which carry over from calculus 1. Polynomials are continuous everywhere. The sum of continuous functions is continuous. Products are too. Differences of continuous functions are continuous, and quotients of continuous functions are continuous where the denominator is not 0. And then you've got all those other continuous functions like logarithms. You take a continuous function of a continuous function. It's continuous within its open domain. You got to be careful of the boundaries. So this one here, look, this is a polynomial of x. In fact, it's the simple function f of x equals x times a polynomial of y. We call this actually a polynomial in 2 variables. But anyways, continuous times continuous is continuous, thought of as individual functions of 1 variable, or because it's a polynomial in 2 variables, you just say it's continuous everywhere. So this is a continuous function. Now, the other thing we needed for doing these problems of maximization and minimization was if we wanted a global max and min, then we needed a continuous function on a closed bounded region. Well, that's what this is, right? X squared plus y squared equals 1 is the unit circle. And here's something that comes into play here that I think the book kind of glances over, but it's assumed here. X squared plus y squared equals 1 is the disk. You might think, or the circle, you might think that less than or equal to 1 is one side of the circle, and it is, but it's not real pointed out. X squared plus y squared is a continuous function, all right? And so where it's less than 1 will be on one side of this thing, and where it's greater, well, I should say, inside the circle, this will always be either less than 1 or greater than 1, and outside the circle, this will always be less than 1 or greater than 1, because it's a continuous function. A continuous function, it can't just jump from less than 1 to greater than 1. It has to pass through equals 1 to get there because it changes continuously without jumps. So what happens is in here, it'll be consistently either less than 1 or greater than 1. All these are the points. These are all the points where x squared plus y squared equals 1. In here, these are less than or greater than, and it can't jump between. So let's just check one point. Let's plug in the origin, 0, 0. and 0 squared plus 0 squared is less than 1. So that's satisfied. I'll shade in this whole area. If I find a single point in here where this continuous function, x squared plus y squared is less than 1, then it will be less than 1 in this whole region here, because these are all the points where it's equal to 1. It can't jump between less than or greater than within this region. So 1 point less than makes them all less than. Similarly, I take a point out here, maybe the point 2, 0. 2 squared plus 0 squared is not less than or equal to 1. So this is not going to satisfy it. And that means all the points out here don't satisfy x squared plus y squared less than or equal to 1. They can't become less than. They're greater. This one's greater than. You can't move around here continuously and change it to less than, and suddenly it has to go through a point where it's equal to 1 since it's a continuous function. So what your hunch might have been is that one side of the circle is less than, one side of the circle is greater than, turned out to be true. The inside of the circle satisfies this and the outside doesn't. And so we're looking at this closed bounded region. What does closed and bounded mean? If you read in the book, bounded means there's some big rectangle, no matter how big, that encloses every point in the region. So I can make a big rectangle that does that. That makes it bounded. Closed means it includes its boundary, right? Well, it includes the circle along the boundary because it includes equals. So this disk is a closed bounded region. And we have a theorem, a continuous function on a closed bounded region has an absolute max and min. This is what we're talking about here. So we're off to a good start. We can actually say they exist. How do we find them? That's one. So when you're finding absolute max and min, I'll just remind you, in calculus 1, you've got a function of one variable. What you say is any continuous function on a closed interval has a maximum and a minimum, and each occurs, and there might be more than one place it occurs, but each occurs either at an endpoint, like here's the minimum, or a critical point that's interior. This carries over here on a closed bounded plane region, right? This is a function of two variables, so its domain is not an interval of real numbers, it's a plane region. On a closed bounded plane region, a continuous function of two variables has a maximum and minimum, and each occurs at a critical point. So those are the theorems we had. Furthermore, what were the critical points for a function of two variables? For here, it was places where the derivative was equal to 0, or the derivative didn't exist if you had a corner in here or something, right? Or discontinuity, but then you couldn't apply the theorem. So here you're looking for the derivative equal to 0 or a corner. Similarly, for a function of two variables, a critical point is a point where both partial derivatives are 0. Partial of f with respect to x is 0, and partial of f with respect to y is equal to 0 at the same point. Or at least one of these doesn't exist. But we still want the function continuous to be able to apply this theorem. Well, this is the polynomial in two variables. The partial derivatives exist everywhere, right? Derivatives of all orders. Almost. So one, we make sure it's a closed bounded region if we're going to find absolute maximum minimum. Two, each one occurs at a critical point. What did we do in calculus 1? We said, well, these are the candidates, the endpoints, and the critical points. And so you just plug every one of them into the function. The largest was the absolute max, and the smallest was the absolute min, because the theorem said there was one, and these are the only candidates. Same thing here. You just plug each critical point into f of x, y. The largest will be the absolute max and the smallest will be the absolute min. So that's how it'll work. And we can apply it to this one. There's their theorems. So we do one, we want to find the, we said it's a closed bounded region. Then step two, we'll set both partial derivatives to zero. So we have 0 equals partial with respect to x, which is y, we said, and 0 equals partial of f with respect to y is x. And so in order for both of them to be satisfied, that's the critical point here, they have to both be 0. This says x equals y equals 0. You have only the origin. 0, 0 is the only critical point. But we have to check the boundary too, right? I didn't finish writing this guy. Each occurs at a critical point in the interior or on a boundary. Like here. All right. So sorry for that run-on sentence there. All right. So this is the only interior point I have to check, but now I have to check the boundary. What about the boundary? This is kind of a tricky one here because it's a circle, right? So how do I check out that circular boundary? What you can do is switch to polar coordinates. What's the equation for the circle in polar coordinates? You can sweep it out parametrically by letting r equal 1 because it's a unit radius circle, and theta goes from 0 to 2 pi. That'll sweep out the boundary once. And now what I want to do is say, what are the candidate boundary points for this thing? I better move this to the other side. I'd hate to, but I think I need to. On the boundary, f of x, y is equal to xy, but in polar coordinates, that's r cosine theta times r sine theta is r squared sine theta cosine theta, which can also be written by the double angle identity. Remember, sine of 2 theta is 2 sine theta cosine theta, so sine times cosine is 1/2 sine of 2 theta. Right? And now along the boundary, r is actually equal to 1. So this is 1/2 2 sine theta. So that's r equals 1 on the boundary. Now what you have is a function that you want to find. What are all the candidates for the maximum and minimum of the function? This is right. This is z equals f of x, y. What's the maximum value of z on the boundary if theta goes from 0 to 2 pi equal to this value? Now this is a function of one variable to be maximized because I got rid of r. To maximize or minimize, we could call this f of theta if you like. Like that. This, we said its derivative equal to 0 a la calculus 1. So we need the derivative of 1/2 sine 2 theta equal to 0. Well, we know how to take the derivative of sine 2 theta. It's 2 cosine 2 theta. So this is equivalently to cosine 2 theta equals 0. And so what are the points at which cosine 2 theta equals 0? Again, theta is running from 0 to 2 pi on the boundary, so that's all we can put in. And we find that this is equal to 0 when its argument is pi over 2 plus a multiple of pi, right? So we need 2 theta pi over 2 plus any integer multiple of pi. But within this restriction, theta has to be between 0 and pi. That's it. Along the boundary, this is the z coordinate, the height of the function that you want to maximize. But because we pick polar coordinates wisely, this is now a function of one variable. And to maximize a function of one variable, you just set its derivative to 0 and seek over the allowed values of theta, what values can you get? So if this has to be between 0 and 2 pi, let's see, this is theta equals pi over 4 plus k times pi over 2, restricted to theta between 0 and 2 pi. And so if you put k equals 0, then you've got pi over 4. If you put k equals 1, you've got 3 pi over 4. If you put k equals 2, you've got 5 pi over 4. If you put k equals 3, you've got 7 pi over 4. And all other values of theta are either bigger than 2 pi or less than 0. So these are the critical boundary points. All the candidates on the boundary where you might have a maximum. So now what you have to do is the last step there, still on, yeah, is you just plug each in. You find the interior critical points, you find the candidates along the boundary, the critical points on the function of one variable here, and you just plug them in. And these points here are where x equals r cosine theta is 1 times cosine pi over 4 is square root of 2 over 2. And y equals r sine theta is 1 times sine pi over 4. Move this. Is square root of 2 over 2. And so what we found is that on the boundary, we have the point square root of 2 over 2 is square root of 2 over 2 is a point we have to check. So I guess it's not. All right. Then if we put 3 pi over 4, it's x equals 1 times, right? It's r cosine theta with r equal 1 on the boundary. Cosine 3 pi over 4. Well, cosine 3 pi over 4 is minus square root of 2 over 2. From trigonometry. And y equals 1 times sine 3 pi over 4, which is plus square root of 2 over 2. Now we've got the point minus square root of 2 over 2 plus square root of 2 over 2. And you go on, so this one corresponds to theta equals pi over 4 on the boundary. This one corresponds to theta equals 3 pi over 4 on the boundary. Then we need to do 5 pi over 4. And if you think about it, there's a nice picture for this. It's starting to figure out, right? The idea is in the xy plane on the unit circle, at those four angles, pi over 4, here you get square root 2 over 2 for each coordinate. At 3 pi over 4, you got this one, minus square root 2 over 2, plus square root 2 over 2. And at the other one, what we're going to get is this one over here, minus root 2 over 2, minus root 2 over 2. And at 7 pi over 4, we'll get square root 2 over 2, followed by minus square root 2 over 2. So those are all the critical boundary points you have to, so we'll just say it, dot, 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 you get minus and minus. And this one you got dot, 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 plus minus. All right, so 4 critical points on the boundary, these 4 right here, plus the, you have from the interior critical points, there's one at the origin. You have to plug in all 5 of those points. So this was the interior one, where both partial derivatives were equal to 0. So these are long problems, but they're kind of neat, I think. And you just plug them in now. It's over. Plug them in and get f of 0, 0. F is x times y. Let's basically say that. Plug into f of x, y equals x, y. When you plug in 0, 0, you get 0 times 0. The value of the z coordinate is 0. If you plug in square root 2 over 2, square root 2 over 2, the critical boundary point, then x times y is root 2 over 2. Root 2 over 2 is a half. Same thing if you plug in minus square root 2 over 2, minus square root 2 over 2. And if you plug in minus square root 2 over 2 plus square root 2 over 2, then you get minus square root 2 over 2 times square root 2 over 2 is minus a half. Same thing you get if you plug in f of plus square root 2 over 2 minus square root 2 over 2. So I plug in all 5 points, and the largest value I got out of 1.2345 that I plugged in was this one. So you say that's the absolute maximum. The smallest number I got is negative. Negative a half is less than 0. And that's the smallest one. So what I conclude then, therefore, you have the absolute max, the largest this function ever gets over the disk, is 1/2, and it occurs at both these points, right? At square root 2 over 2, square root 2 over 2, and then minus the same. Absolute min smallest number was minus a half, occurs at the other 2 boundary points, and an interior critical point just didn't happen to be either the absolute max or min. All right, so there's your answer to the problem. This is the absolute maximum occurs at these 2 points. This is the absolute minimum occurs at these 2. You feel okay about that one? Can you do something like that? These are kind of long, but you know, they're like a fairly straightforward process. Okay, so that's absolute max and min. We should do one more example, I think. Don't you? Do one more example. How about this one? Suppose I want to maximize f of x, y equals 2x plus y minus 3xy, this time on the unit square. In the first quadrant. 0 less than or equal to x and y less than or equal to 1. So this time, I think it really helps to draw domains. We have this domain, 0 to 1, 0 to 1. And within this square, and we're including the boundaries since we allowed equals, we're going to say for what values of x and y in this domain of this function are we going to get the maximum values and the minimum values? Right. Well, once again, it's closed because you can enclose it in some rectangle, no matter how big, right? It's bounded because it does. Sorry, that's bounded because of that, and it's closed because it includes its boundary. So this is a closed bounded region. We can apply our theorem and just say all the absolute max and min, if there are any, occur either at an interior critical point or along the boundary. So for the interior critical points, I'll set the two partial derivatives to 0, noticing that this is again a polynomial in two variables, right? You can have, right, in general, what you have is a bunch of terms, a constant times x to a power times y to a power, which can be 0. And if you have a whole bunch of these summed together, like k and m run up there, and then you've got a polynomial in two variables. So this is a polynomial in two variables. And it's continuous and has derivatives everywhere of all orders. So we can set those partial derivatives equal to 0. Partial with respect to x is 2 minus 3y. Partial with respect to y is, let's see, 1 minus 3x. All right, so what are the interior critical points for this one? There were both these things are equal to 0. Well, you're lucky on this problem. Some of these are much harder. I told you often you'll get nonlinear equations here that are not so easy to solve, but these are two linear equations, right? They're very easy to solve. And so this one says y equals, if this is equal to 0, it says y equals 2/3. 1 minus 3x is equal to 0, that says x equals 1/3. So there's only one critical point because you have to satisfy both these. 1/3, 2/3 is the only interior critical point. Okay, so start drawing these in color, probably stand out better. 1/3 by 2/3, so it's back here. Right? Now we've got to look at the boundary points, right? What are the boundary points where we might possibly have a maximum of it? Once again, you write parametric equations for the boundaries. Now these are straight line segments, so they're pretty easy. But we're not going to go to polar coordinates because this time it's, you want rectangular coordinates since you got a special case of a rectangle in that square. So what I'll do is break this up into 4 pieces. C1 is this piece. We could say C2 is this piece. We could say C3 could be this piece, and C4 could be this piece. And we can have the boundary curve C is in the union of these 4 curves, right? And so if I find if I write parametric equations for all 4 of those, I can find all the critical points of the boundary that I need to check. So for C1, what I'll do is say, oh, this is really easy. Y is equal to 0 and x has to go from 0 to 1. So I'll make parametric equations. X equals t, y equals 0, and let t run from 0 to 1, and we'll sweep out the first unit of the x-axis there. And we'll say along this one, then what do we do to find out if there's what points we need to check? We say along C1, we can plug in t for x and 0 for y. We get f of x of t, y of t, a function of one variable now along the boundary, is 2t plus 0 minus 3t times 0 is just 2t. So as you move along the boundary, you're trying to, it's over a little. As you move along the boundary, you're trying to, this time we're just finding the maximum. So we're trying to maximize 2t. Let's find the max and the minimum. So the only critical points are at the end, right? This one, if you set the derivative equal to 0, right? This is now a function of one variable. Derivative equal to 0 says that 0 equals 2. And there is no point. So you just have to check the endpoints. So we have to check picture back, that's off the screen now. I have to check the two bottom corners of the square here. Check 0, 0. And 1, 0, the endpoints only. Because there was no interior critical point along the boundary. Now we'll say along C2. This can get tedious when you have to break these up a lot. Now C2, I knew this back's coming up. You can't see online. Distance on there. Yeah. All right, so along C2, x is equal to 1, and y can run from be equal to t, run from 0 to 1 to sweep out this boundary of the square. So let's say along C2, x equals 1, y equals t, and t runs from 0 to 1. And now we'll say the function f as a function of t along this boundary is equal to, now you replace x with 1 up here, 2x plus y, 2 times 1 plus y is t, minus 3xy is minus 3 times 1 times t, is 2 minus t. 2 from here plus t minus 3t is 2 minus t. Once again, this one, if you set the derivative equal to 0, find its interior critical points, you find out that 0 equals minus 1, there are none. But you have to check the endpoint still. So you check endpoints of the second segment, which is 1, 0, and 1, 1. So now I'm going to add this one. I've already got 1, 0 from the last one. Check endpoints. 1, 0, and 1, 1 along that boundary. And you do the same thing for the other two boundaries, right? See if I can get this in. Along C3, you look at the top of the square there. Now you have y equal 1, and you know that x be equal to t, or let's call it 1 minus t, y equals 1. And now as t goes from 0 to 1, this runs from the 1, 1 point back this way. You can just make make it easier and go the opposite direction. We don't need to keep a consistent direction. We're not using one of those theorems from last semester. So we can just run it this way, actually. We just want to check the boundary. So let's let x equal t, just be simple, y equal 1. And now along that boundary, what do we've got? We've got f is equal to 2x is 2t, plus y is plus 1, minus 3xy is minus 3 times t times 1. So it's 2t minus 3t is minus t plus 1. So it's t, it's 1 minus t on this one. So along C3, again, you look for the critical points along the boundary by setting the derivative equal to 0. But that's makes 0 equal -1. There are no critical points, so you just have to check the endpoints. And the endpoints are at 1, 1, and 0, 1. And now we also check C4 similarly. I'll just say dot, dot, dot. We won't get anything new because what we're finding is that this function is so simple that the only way we can make its derivative equal to 0 along the boundary curves, given parametrically, is at the endpoint. So we have 4 critical points along the boundary, the corners of the square, and 1 point, 1/3, 2/3 within the square, an interior critical point. We have to check these 5 points. Well, to check them on this method, right, we just plug in and see which one's the biggest, which one's the smallest, because in the closed bounded region, we know one of those is. Only 5 to check, we can do it. Right? Plug each in. And we'll take f of the first point, 1/3, 2/3. Is, well, f was 2x plus y, so 2x plus y minus 3xy, so minus 3 times 1/3, 2/3. And let's see, we've got 2/3 plus 2/3 is 4/3. These cancel. Minus 2/3 is 2/3. So the z coordinates equals f of x, y is equal to 2/3 at this interior critical point. Then we plug in the points along the boundary, which turned out to be the 4 corners. So we take f of 0, 0. If you plug that in, you can see, right, 2 times 0 plus 0 minus 3 times 0 times 0, and you get 0. Then f at 1, 0, f at 0, 1, and f at 1, 1. At 1, 1, we've got 2x plus y minus 3xy. 2 plus 1 is 3, minus 3 is again 0. And f of 0, 1 gives us 2x plus y minus 3xy gives us 1. And finally, f of 1, 0 gives us 2x, 2 times 1, plus y is 0 minus 3 times x times y gives us 2. Looks like it. All right. So now you just look through all these numbers here. I guess I shouldn't have boxed this one. The largest is the absolute max and the smallest is the absolute min. Here's the largest number I got. So this is the maximum, the global maximum. And the smallest was 0. So these two are jointly the absolute minimum. So finally I say, therefore, I get an absolute max of 2 at the point where 2 occurred, 1, 0. Absolute min occurs of 0 at 2 points, at 0, 0 and 1, 1. That gives you a pretty good smattering of problems. This is what you have to do on the other one. Some of them are a little longer than this. Maybe we'll do some more sometime. But you find the interior critical points by setting the partial derivatives equal to 0 or finding places where it's not, where they don't exist in there. You find the critical points along the boundary by writing parametric curves. And then you just plug all those points in. The largest is the max and the smallest is the min. That's how you solve the absolute max and min problem on a closed bounded region. And then the other one we did last time, we said, suppose instead you want relative max and min on an open region. Then what you did was you set the partial derivatives equal to 0 and applied the second partials test to each. So that's what we have. It's 2 techniques. One for relative extrema, that's similar to what you did in calculus. One function is a 1 variable. One for absolute max and min, which is similar to the second derivative test from calculus 1. Sometimes you have questions. I appreciate input. Sometimes I go too fast or don't explain something. All right, well, then we're going to charge ahead. The next section is on Lagrange multipliers. And this is actually going to finally finish this long chapter. How about that? You might think, why are we changing gears? Isn't there some more maximum and minimum we can do? Yes, there are, and this is it. What we've been doing is finding these relative maxima and minima and these absolute maxima and minima. This one we're going to do constrained maxima and minima. So consider this kind of a problem. Maximization or minimization of a function of two variables subject to a constraint. Curve given in the form g of xy equals 0. Actually, it can be g of xy equals c more generally, because you might subtract c over and it's the same thing, but book puts it as g of xy equals 0. Or just a general constraint curve given implicitly like that. Right? Well, if f has continuous first partial derivatives, on an open region, just meaning a region that doesn't include its boundary, containing the constraint curve g of xy equals 0. This is an open region. This puts it in its interior also. And the gradient of g is not equal to 0 anywhere along the curve. Let's call this curve C. Along C. And F has a constrained maximum or minimum. So it's an absolute maximum in again, but it's subject to a constraint. Then it occurs at a point in the plane, a point in the domain, where the gradient of F is equal to some number lambda times the gradient of G. Where lambda is a constant called a Lagrange multiplier, after a famous mathematician named Lagrange. I think I remember as one of the mathematicians in my mathematical heritage, where you go back and you say, you had this advisor who had this advisor who had this advisor who had this advisor. He was advisor to one of my advisors way back there. who got their PhD. So anyway, lambda is a Lagrange multiplier. It's just a constant. So what this says is if you have a constrained maximum under these nice conditions, it's where the gradient of f is a multiple of the gradient of g. They point in the same or opposite direction. And here's just an outline rather than trying to do a detailed proof, which is too much for this class. We just try to motivate things a lot with the idea that when you get more mathematical maturity, if you really wanted to prove it, you could. We have a class called real analysis where you go back and all these theorems that we waved our hands at and didn't actually prove. You can go through and they'll go back and prove some of those. Sometimes they'll do that a little bit in advanced calculus too, depending on who's teaching it. There's an applied course where you learn more material or a pure course where you do more proofs. All right, so here's the idea without doing the proof. In the XY plane, there's a plane region, an open plane region that contains the curve g of xy equals 0, right? And so you want to have an open region that contains, let me draw that curve in another color. The constraint curve, g of xy equals 0. And now the problem is this. It's always nice to know what the problem is, doesn't it? Isn't it? The problem is this. You're given a curve, z equals f of xy, some function like this. That's sitting over some plane region down here. So this is the domain here, and this is its curve C, given implicitly by g of xy equals 0, and so this is C here. Instead of saying, oh, what's the maximum value it takes on, what's the minimum value it takes on, the highest and lowest point on the surface, what we're instead saying now is you're subjected to walking along this curve here. I'm sorry, this is C here. This is the region. This is the open region. And this is C within it. You're subjected to walking along this curve, and subject to that you walk along that curve, what's the highest point over the curve? So now what you have to do is consider up on the surface here, f of xy for just these points xy that are on the constraint curve. Now what's the highest z value? There's some point here. This is your absolute maximum. The highest point, not on the surface, but on the surface subject to the restriction that you can only move above this curve here. And then there's a lowest point somewhere, maybe here. And here's the minimum. And the idea, I really like thinking of it this way, is that you're like a mountain climber saying, how high on the mountain can I go subject to the constraint that I have to walk along the trail, right? I can't walk off through the cactus or something. And so here's my map. And my map says I have to stay on this trail. And what's the highest altitude I get to along the trail? This is my trail, and this is the real mountain sitting up here. And I go up around the trail, and here's my highest altitude I got to as I walked along the trail. And here's the lowest. But this is my map in flat XY space. And this is the function, z equals f of xy. So that's the idea of constrained maximum and minimum, is subject to walking along the trail in the xy plane, the domain. What's the highest z value you get? Z equals f of xy over above that trail on the surface. Does that sort of make sense? I hope. Well, when you consider that constrained problem, the Lagrange multiplier theorem there says that it occurs where the gradient of f and the gradient of g are multiples of each other. So they point the same or opposite direction. They're parallel. Where is that likely to be? Well, what happens is, remember these level curves? This mountain, if you project it down to the XY plane, it has level curves like this and like this, where you have the same altitude all along the mountain. Here's another one. And so you get these level curves down here. And the idea is that when am I at the highest point I'm ever going to be on the mountain? Maybe it looks like this one here. Well, it's when the, maybe I should draw it here. It's hard to draw this stuff. So here's some level curves of the mountain that's sitting above. These are level curves. Of f of x, y, where you take these traces up here and project them down into the plane, right? This is a trace, z equals a constant. You just drop it down here and this becomes a level curve in the xy plane. It's the same curve, just out on the same plane with the other curves. How do you tell where you're at the highest point on this mountain? Well, it'll be at a point like this, where these things just become kind of tangent, assuming it's a differentiable curve. Where these become tangent, this is a level curve. See, so this might be the lowest isoplet. This is the next isoplet being a curve where the altitude is constant. So this is the level curve. The lowest altitude, if these are higher and higher altitudes with each ring, is right here where they're tangent, right? Because right, this is the lowest level curve that you struck with the constraint you have to walk along this blue path. So the blue path is the map of your trail, and the green ones are level curves or isoplets of the mountain that you're walking on. And when you get down to the smallest level curve, that's where your minimum is, in here. At this x0, y0. And you notice that at those points, these become tangent, which means that when you take the gradient of f, the gradient has to be perpendicular to the level curve. It should point the other direction on, because this is, so it points in the direction of its greatest increase. Here's the gradient of f. And then g, what about the curve g? Well, because we define this curve implicitly by g of x, y equals 0, right? G of x, y equals 0 is a level curve of z equals g of x, y. So its gradient is also going to be perpendicular to the trail. So there's the gradient of f is perpendicular to its trail. The gradient of g is perpendicular to its trail. It might point the same or opposite directions depending on whether g is bigger in here or bigger out here. But here's gradient g. And the idea is when these are parallel, either the same direction or opposite, that's when the two trails are going to be tangent. That's where you're going to hit your lowest isoplet. Similarly, over here, what's the highest altitude you get to? Well, it's when you touch this isoplet, right? This altitude isn't the highest you get to. This is the highest you get to. You just touch that. And once again, it's where they're tangent. So maybe the gradient of g points this way. And gradient of f points towards higher altitude, so maybe it points this way. But the idea is they're parallel, right? Gradient f. And that's what you try and make rigorous in the theorem, as you say, have to be parallel, you know, presuming that this thing, that these things become tangent because there's smooth curves here. All right, I hope you can see that. I drew so many things over there, it's hard to see anymore. Maybe I should draw it again. Almost all the shadings and everything. I'm sure you can see this. Here's the trail. You have to walk the map of your trail in the XY plane, right, which is this one here. The actual trail is up here on the mountain. This is mountain z equals f of xy. And as you walk along this trail, there are level curves of the mountain. These are the curves corresponding to these things here, the traces up here of level altitude. And somewhere along the way, you get to the lowest altitude. Here's the lowest isoplet I touch. The gradient of this curve is g of xy equals 0. It's the trail. And these other curves are level curves. The green ones are level curves. When you're moving along the trail, the smallest isopleth you ever go touch is this one right here. And so this is the maximum height, assuming these are getting higher and higher altitudes with the rings. Max, we can call it whatever, x1, y1. Is again where these are tangent. Consequently, the gradient to this level curve has to be perpendicular, we proved before, so points say this direction. The gradient to this one, because this is the level curve of the function g of xy, also has to be perpendicular to it, and then they're parallel. So you get the maximum where they're parallel, and you also get this minimum where they're parallel. Up here, right, gradient of f maybe points this way, and gradient of g maybe points that way. Sometimes they're the same direction, it just depends. So that's the idea of the Lagrange multiplier theorem. Then you go to prove it, it probably takes you 10 times as long as that. All the details. So now we can try and find this constrained maximum problem subject so that you walk along the trail on your trail map here in the XY plane. You're actually traveling up here. What was the highest altitude on the mountain you got to? What was the lowest altitude on the mountain you got? Think of it like that. And here's a Lagrange multiplier problem. Let's try to maximize the function f of xy equals 2x plus 5y, subject to the constraint that you have to lie on this curve, x squared over 4 squared plus y squared over 3 squared equals 1. It's really fun to draw these things out. It makes a whole lot more sense because that looks like a bunch of jumble, doesn't it? Well, what am I saying here? Maximize this function subject to this constraint. Think about what this constraint looks like. What does that look like? You plot that in the XY plane. Oops, leave a little more room. Remember what this is an equation for? Anybody? It's an ellipse. X squared over a squared plus y squared over b squared equals 1. Remember that from last semester? Of semi-axes 4 and 3 at the origin. So you go down an x-axis. 1, 2, 3, 4. 1, 2, 3, 4. Between 4 and minus 4. And the y-axis between plus and minus 3. 1, 2, 3. And this ellipse, I have to draw it. This is the constraint. Right? This ellipse is actually a constraint curve. You have to walk along this elliptical trail. Now what you're trying to do, am I getting off the thing again? I am. What you want to do is subject to the idea that you walk along that trail, you want to maximize this function. What kind of function is this? Z equals 2x plus 5y. It's a linear function, right? Z equals ax plus by plus c is always a plane. And so this is a plane. If you make any equation like this, right? Ax plus by plus c, z equals d, with a, b, and c not all 0, this is a general form for a plane. So you can put this in this form. Z equals 2x plus 5y fits this form. So this is a plane in 3 space. This is an ellipse in the domain of this function in the plane. And so what you're being asked to do now, this all makes more sense when you draw it, is consider moving around this ellipse in the XY plane. And the surface over the top is the plane, that's something like this maybe. here's the plane, z equals 2x plus 5y in 3D. This is the ellipse in the xy plane in 2D. And you're asking, what's the highest altitude I get if I walk along Mount z equals 2x plus fy plus 5y over where I'm marked on the trail map? Well, right, when I take z of each of these, or f of each of these points, what I trace is a big oval up over this, and these are the actual altitudes I go to. So the highest altitude I go is somewhere up here. That'll be the maximum. And then the lowest altitude maybe is here. This will be the minimum, right? The maximum, minimum are the dependent variable z. And then, but you're also interested in where do they occur, right? There's some minimum here. Oops, not here. Here is the minimum. Some x0, y0. And at this point here, it's some x1, y1. We'll get a maximum. So let's see if we can find those points. What do we need? All right, by the Lagrange multiplier theorem. And what you do technically, this is not written in the form g of xy equals 0. It's written as g of xy equals c, which is just as good. You say this is equivalently x squared over 4 squared plus y squared over 3 squared minus 1 equals 0. And this is a problem, g of xy equals 0. So that's what we call g in the Lagrange. And then this one is the one we're trying to maximize. If you're trying to maximize or minimize a function subject to a constraint like this, that's for the Lagrange multiplier theorem. So by the Lagrange multiplier theorem, we need to use the gradient of f. What's the gradient of f? Well, it's the vector of partial derivatives, right? It's partial of f with respect to x, which is 2. Partial of f with respect to y, which is 5. And so we need to use that. We also need the gradient of g, right? We're going to set one equal multiple of the other. So what's the gradient of g? If this is g of xy, partial with respect to x is 2x over 16 is x over 8. And then partial of this function with respect to y is 2y over 9. So there's gradient f, the function you want to maximize or minimum. Here's gradient of g, the function that provides the constraint, g of xy equals 0. And the Lagrange multiplier theorem says you can demand that gradient of f equals lambda gradient g for some constant lambda that we call a Lagrange multiplier. So we write these two are equal. We say that 2, 5 at a point at the point of maximization. We know this is going to hold. So 2, 5 is going to be equal to lambda some number of times x over 8 2y over 9. So how can we make that so? Two vectors are equal if and only if their components are both equal, right? So we'll have both components equal. This says 2 equals lambda times x over 8. And 5 equals 2 times 2 lambda y over 9. Lambda x over 8. So we need both of these things to hold. And you know what happens if you just write down gradient of f equals lambda gradient g, you get stuck on all these problems because it generally has an infinite number of solutions. The reason being you've got 3 variables, x, y, and lambda, and only 2 equations. We don't usually reduce that to a finite number of points that way. So usually you just be stuck there unable to solve it. What you do is you add one more thing, and that's the constraint equation. The constraint equation is x squared over 4 squared plus y squared over 3 squared equals 1. 3 equations, 3 unknowns, typically reduces this to a finite set of points to check. Then I can just check them, see. So here's the Lagrange multiplier theorem, and here's the constraint. Between these, I can eliminate the variables. And again, you get nonlinear equations here in general. These are pretty tough to solve. So they try and give you some in the book that you actually can solve. What can we do to get this? Can you see? Just generally, what you do with these is by hook or by crook, you substitute in until you get an equation in one variable. So I can see how to do that here. On this one, I can solve for x and say this is x equals, let's see, 16 over lambda. Right? Multiply by 8, divide by lambda. This one I can solve for lambda, for y, and get y is 45 over 2 lambda. Right? And then I can substitute those into this one, right? And I'll get this down to just a function of lambda. So I'll get x squared is 16 over lambda squared. That goes by 4 squared. Plus y squared is 45 over 2 lambda squared over 3 squared equals 1. Now I've got an equation in just lambda. I can try and solve that. Boy, I need some room here. Well, let's say, so now this one says the 16s cancel and you just got 1 over lambda squared on this one, right? But on this one, you're not so lucky. Some of it cancels. The 45 over 9 is 5. Oops, wait, it's 45, not 45 squared. Wait a minute. Is that right? X equals 16 over lambda. Yeah, that doesn't all cancel, does it? So I guess this is 16 over lambda squared plus, oh boy, so this is going to be 45 times 5, 225. 225 over twice lambda squared has to equal 1 when we simplify those quotients. All right, well, I didn't write down what lambda is on this one. I suppose we can figure it out from here. Wrote down the other answers. Okay, so now this one says we can solve for lambda. Multiply through by 2 lambda squared, and we can get 32 plus 225 equals 2 lambda squared. Multiply through by 2 lambda squared. And apparently 257 equals 2 lambda squared. So lambda equals plus or minus the square root of 257 over 2. I don't remember quite getting this number. Yes, let's see. So I'm getting quite the right number here. I'm missing a factor 2 here or something. What I'm supposed to get here is 17, and I'm getting square root of 257 over 2. We got 2 equals, sure I did this right. X over 8. 2y over 9 is 2, 5. X is 16 over lambda, y is 45 over 2 lambda. The squared plus the squared. So that one becomes 16 over lambda squared. Plus this one becomes 45 times 5 is 225. Oh, it's 4 lambda squared here. That's, I didn't put 2 squared. That's what's going on. 4 right there. And now, if I multiply it through by 4 lambda squared, this becomes 64 plus 225 equals 4 lambda squared. So all I did was I plugged these two into this one and got an equation of just lambda squared. And now, good, this is 289, the square of 17. And so you get lambda from this equals, lambda squared is 289 over 4. So lambda is plus or minus 17 halves out of that by square rooting, adding these and square rooting. So there's lambda. Well, once you know lambda, you know x and y, right? Because x is 16 over lambda. I'm going to turn that over here. I tried my best to get it in before the end, but I couldn't. So now, x equals 16 over lambda. So for lambda equals plus 17 halves, I get x equals 16 over lambda equals 32 17ths. And y equals was equal to 45 over 2 lambda. Lambda equals 17 halves is 45 17ths. There we go. And so one of the candidate points is has coordinates 32 17ths, 45 17ths. Also, we have another value of lambda for lambda equals minus 17 halves. You get the similar point, minus 32 17ths, minus 45 17ths. Those are the two candidate points. So what do you do with those? Here's what you do, and again, this never appears in the books, but they just assume you sort of have this intuition. Let me look back at the picture here. Is it on this picture here? Just barely. What we know is that we have, since we have a plane up here and a continuous curve down here, this is a continuous curve right here in 3 space. A continuous closed curve like that has a maximum and a minimum. So we know it has a absolute maximum and an absolute minimum. Those 2 points have to give it. The Lagrange multiplier theorem says that the only candidate points for these two are those 2 points, and we know it has them. So those are the answers right there. You don't have to say that on your papers, but I just wanted to point out that whichever one gives the largest value is the maximum, and whichever one gives the smallest is the minimum. Well, you're maximizing 2x plus 5y, so you want these positive. So the maximum is z, if you like, equals twice 32 17ths plus 5 times 45 17ths. Occurs at the first point, 32 17ths, 45 17ths. And the minimum occurs at z equals 2x plus 5y with this one. Twice minus 32 17ths plus 5 times minus 45 17ths. And it occurs at the second point. So there's the trick. If you have relative extrema defined, then you find the critical points and apply the second partials test to each. If you have global maxima and minima defined, then you try and do it on a closed bounded region. You check the interior critical points and you check the candidate boundary points just by plugging them all in. But if it's a constrained maximum or minimum, you just have to decide which of the three it is. Then you apply Lagrange multiplier. You set gradient of f equals lambda gradient g. That together with the constraint equation finds you these candidate points that you plug in. That's it. Now you're experts on maximization and minimization. We'll probably do one more problem of those next time. I didn't get to a couple examples that I wanted to. I need to put the homework up, don't I, before we go? Otherwise, you'll have nothing to do this weekend. So let's see. On camera, there we go. 13.9. I gave you 13.8 last time, right? 13.9. Look at 1, 5, 7, 9, and 17. I'm going to add another one because they left something out in this book that I really want to include. What if you have more than one constraint? It's kind of neat, but I think we should cover that also. So we'll do all that next time, and I'll get your test back next time. I'm sorry I don't have them tonight. Still trying to catch up my makeup test. Thank you very much for coming in tonight, everybody. Thank you.